Okay, now we've been working on graphing this function. And, yeah, we already either found the y-intercept or found the x-intercepts pretty quick. Okay, now, people who found the y-intercepts didn't find the x-intercepts right away, but when I prompted them, they did, okay? And then we talk about the y-intercept. Okay. So if you get the y-intercept, x has to be 0. If x is 0, then this gives us -3, this is +2, this is -5, right? Okay. So we multiply that out, and we get 120. So we're going to do that. The x-intercepts occur when y equals 0. Now, how's y going to equal 0? The only way y can equal 0 is if this is 0, or this is 0, or this is 0. You've got to understand that logic. Okay, you don't just remember, okay, I just take the opposite of all these numbers, because sometimes these polynomials have factors that aren't as obvious. We'll talk about that too, but there we have the strategy for finding the x-intercepts. So pretty quick, we find point 0, 120, because that's what we get when x equals 0. X is 0, plug it in, and get 120. That's the y-intercept. And we then find that y is 0 when x is -2, when x is 3, when x is 5. So we've got to do a graph through these points. Okay, now there are a lot of ways a graph can go through points like this. I'm just going to sketch another graph with just a few points on the x-axis, a point on the y-axis. Okay. Now, what's this graph look like? It can look like a whole bunch of different things. I mean, it's all going to look like one of them for a given function, but there are a whole lot of different ways this graph can look. It could come down here, go up here a little way, then come down here, come up like this. It didn't do that particularly well, but it could look like this. Okay. It could also look like this. Well, botching that up. Let me just start again. Okay, so looks something like this, not very well drawn. Looks something like this. It could look like this. So, you know what I'm thinking. Apparently that wasn't a nosebleed earlier. I haven't had a nosebleed in decades. Okay. Yes, that's part of my brain that stays oriented. So, okay, well, in any case, it could look like, oh, it could look like this. Okay. Or it could look like a little bit of fun, but let's try one more. look like this. Okay. Now, look at the red graph here. Here it kind of looks like a parabola close to this point. Kind of looks like a parabola close to this point. Okay, because it actually is very close to being a parabola near those points. Now, when you move away from the points, it doesn't look like a parabola anymore. This thing comes down here and then it turns around. Parabolas don't do that. Parabolas just keep getting steeper and steeper. What's it look like at this point? Well, that's what a cube looks like. Is your cubic graph. Well, it looks like this. It actually completely flattens out at the very instant it goes through the origin. Just for that instant. And you can see how that works if you do an accurate table. Okay, well. Question then is, what is this bracket? Okay, we could come down here and up through here, down through here and up through here. Okay, this. Okay, or we could come up through here. Go up through here and down through here and up, and that's where most people are going to drop. And that's pretty much what it does. The only difference is we have this x plus 2 cubed. And this is the factor that gives us 0 here. So it's going to act like a cubic graph does. This goes through this point. It's going to go through the x-axis the way a cubic graph does. I could say more about it. I could show you why. But you just accept the fact that it does. So our graph. I'm going to finish it just yet. We've got a point here, a point here, a point here. So, I'm going to flatten it out here. I didn't flatten it out very well. It's so hard to chalk that on the board. Okay, but it's going to look something like this. Now, the next question is, what happens out here? Does it just kind of do this? And over here, does it do this? Around a little bit. Okay, what does it do? So there we have to look at the long run behavior. And that's the first thing we did in the first section of the chapter. We looked at the long run behavior of power functions. Do this, let's just go into a little bit of detail. Here we need to be able to expand this. We need to be able to multiply all this out. That's a little bit of a pain. Matter of fact, it's kind of a big thing in this case. Okay, to expand this, we have to multiply x plus 2 times x plus 2 times x plus 2. That's going to give us x plus 2 cubed. Well, when we multiply that, yeah, and we already got a good instinct of that. Got to multiply 2 of these. Start with, and then we can multiply by a third. So that equals x plus 2 times x multiplied by x plus 2, because x plus 2 multiplied by this thing is x times this thing plus 2 times this thing. That's x times x plus 2 plus 2 times x plus 2. That's a distributive problem. Okay. Now, if we multiply x by x plus 2, we get x squared plus 2x. Multiply 2 by x plus 2, we get 2x plus 4. That gives us x squared plus 4x plus 4. Then we multiply by that. Multiply that by x plus 2, meaning multiply x times this. Plus 2 times this. And that gives us x cubed plus 4x squared plus 4x plus 2x squared plus 4x plus 4. And then finally, that equals x cubed. We've only got one x cubed here. We've got 4x squared and 2x squared. That makes 6x squared. Plus 8x plus 4. And there's the cube of x plus 2. So we can now replace this x plus 2 cubed by x cubed plus 6x squared plus 8x. Now it's not 4, 2 times 4. Somebody tell me what 2 times 4 is. It's not 4. Yeah. Okay. Started thinking ahead again. Okay, it's 8. And that's times x minus 5. And what do I do with this? Well, multiply this by this. So that's x times all this minus 3 times all this. And that's multiplied by x minus 5. Every time all my pretty colored graphs. Okay. Multiply that out. Well, multiplying all this by x means actually the 4 plus 6x cubed plus 8x squared plus 8x minus 3x cubed minus 18x squared minus 24x minus 24. All that times x minus 5. Well, that equals x to the 4th. We got a 6 and a negative 3 on the x cubed. That's going to be 3x cubed. 8x squared and negative 18x squared is negative 10x squared. 8x minus 24x minus 16x. And then minus 24. And we get to multiply all that by x minus 5. So this takes a little while. Okay. So just adding all this up, give us this. And then we got one more step. I'm not going to do that one more step because I don't actually care all that much what this thing is when it's expanded. It's not going to help me graph it. The question is, what's the highest power of x that I'm going to get out of this? Well, 2, 3, 87. You don't have 87 figures. So if you get it's not that high. What's the highest power we're going to get when we then multiply all this by x minus 5? Well, I can give you that. I multiply x by negative 10x squared. What's the power going to be? What's x times x squared? X, what power? Can't see your fingers are all. Okay. Now, if I multiply x by x squared, I'm going to get x cubed, am I not? Okay. If I multiply x by negative 24, what power do I get? which is the first power. Yep. Okay, I multiply x by x cubed, what power do I get? You get the fourth power. Because looks like we probably need to write this down, because they're the instant responses. For example, x times x cubed means what? Means x multiplied by x times x times x. Okay. And how many x's do I have there? I got 4. Okay. That's why x times x cubed is x to the 4th. Now, I've been assuming everybody knows that, but most people had trouble telling me what x times x squared was. Okay. Yeah, when you see x times x squared is x times x. You multiply it by x, now you got 3 x's multiplied by that. And it's not a rule that you learn temporarily. Okay. It has a meaning, and it means this. And if you understand the meaning, then the rule makes sense, and you don't really need the rule anymore. Okay. So we gotta have that. So again, my question is, what's the highest power of x that we're going to get out of this? Okay. People are not seeing the distributed law. Some are, most aren't. So I'm going to state the distributive law in terms of aardvarks. Okay. And instead of writing out the word aardvark, I'm going to draw an aardvark. Now, I have no artistic talent, so my aardvark might look like a SUV. I don't know. Okay, but I know it's got 4 legs, it's got a tail, it's got a snout, right? Okay, so my aardvark. We go, there's a snout, there's an ear, there's a curly tail, curly tail. Okay, and it's got 4 legs. Okay. A long time. Okay, there's an aardvark. Okay. Now, if I multiply an aardvark by x plus 8, is that equal? Well, the aardvark is multiplied by x, and the aardvark is multiplied by 8. So we have, let's say, I don't have room for that detail. There's my aardvark. Okay. Times x. Yeah, every aardvark is going to look different than last one. 8. Okay. I think I can draw that thing faster. I can write the whole word aardvark. I can run it fast. And that's the distributive law. Multiplication distributes over addition. Okay. And it works if the x plus 8 on the other side. And we saw that like here. So this x plus 2 times this whole aardvark here is x or multiply this by this. Okay, so let's say Here's X plus 2, and here's our aardvark. We multiply X by our aardvark and 2 by our aardvark. There's X times the aardvark plus 2 times the aardvark. Okay. And once we did that, then we multiply X plus 2 times this big old aardvark. Okay. And we multiply okay, well, actually, this aardvark, we simplified this. Multiply X plus 2 by this aardvark, and now we have X times the aardvark plus 2 times the aardvark. And we work all that out and add up our like terms and so forth. Okay, well, that's a distributive law. And people aren't seeing what to do with that X minus 5. Okay, so this is just an aardvark times X minus 5, isn't it? Here's your aardvark times X minus 5. So aardvark times X minus 5 equals Picasso has no advantage on me. I can go through okay, it's going to be okay. Aardvark times X minus 5 is aardvark times X minus aardvark times 5. Aardvarks are getting more and more abstract, but you understand the point here. Aardvark times X minus 5, aardvark times X minus aardvark times 5, right? So when you write this out, you write out this thing instead of the aardvark. Okay, this whole thing here times X, and then this whole thing minus this whole thing times 5. Okay. So we really have to do that. And then the question is, what's the highest power of X that you're going to get when you do that? Okay. So when you multiply X by all this, what's X times X to the 4th? What's the power? X to the 5th. Okay, that's going to be your highest power. Now, when you look at this, you don't have to multiply all this out to figure out what the highest power is going to be. You know that you're going to get X out of this one. And you know you're going to get X cubed out of this one by the time you multiply this by itself 3 times. And you're going to get an X out of this one. Look at the pattern here. Every time we multiply down here, every time we did one of these calculations, we got another power of X, right? So we multiplied X plus 2 times X plus 2. Since this X is going to be multiplied by this X, we're going to get an X squared. We don't need to even worry about the rest of it unless the problem says, well, expand this, okay? Okay, so multiply X by X here, we'll get an X squared. Then when we do the next step, we're going to multiply X by this X squared and a bunch of other stuff. Then we're going to get an X cubed. Okay, so we're going to get an X to the 5th out of this. We understand how to expand it and expand a few of these things, and very quickly understand how to find the highest power. It will. I'm going to turn my abstract aardvark upside down here. So I'm going to be able to say now. Okay. So far, we know the graph looks like this. What we don't know is what it looks like if we zoom back. Well, If we zoom back. We know that y is going to have to equal x to the fifth, then plus a bunch of other stuff. We also know that the highest power tells us what the graph is going to look like when we zoom back. I'm talking about why that is, but I'm not going to talk about why. I'm just going to say you zoom back and what you see is the highest power in width. Talk about that. Talk about that. It's too. Okay. So what's the graph of x to the fifth look like? Can you stretch me a quick graph of x to the fifth? Don't mean make the table, although you could. But what's the shape of the x to the fifth graph going to be? Well, again now. X squared graph looks like this. The x cubed graph looks like this. Now you could make a table for the x to the fourth graph. Tell me what happens. What's negative 2 to the fourth? Is it positive or negative? Negative 2 times negative 2 times negative 2 times negative 2. It's going to be positive or negative. It's going to be positive. Negative 2 times negative 2 is positive, right? And this negative 2 times negative 2 is positive. So now you have, well, it's going to be 4 times 4, it's going to be 16, it's going to be positive. You've got 4 minus signs when you do the fourth power. In 4 minus signs, you can match them up in pairs. And any pair of minus signs, your multiplication is going to give you a positive. Okay, so the x to the fourth graph is going to have a lot of the same behavior. It's going to be positive over here, it's going to be positive over there. It'll look like this. We talked about it. There it is. It's pretty flat in the middle. And the higher the power, the flatter it gets. And the reason for that is, well, what's 1/2 to the fourth power? It's 1/16. Okay. Which is really close, pretty close to 0. So it pulls the graph way down here at negative 1/2 and 1/2. Whether you understand that or not, that's what's happening. Okay. Then the x to the fifth. If you do negative 2 to the fifth, you got 5 negative signs. You pair 2 of them up. If you pair 2 more up, you still got 1 left over. You got a negative. So you're going to have a negative. And it's going to be easier to draw from this side here. It's going to be like this. Pretty flat in the middle. Okay. Now, this graph is going to look like this if you zoom back. And as I've said before in class, the wiggles are in here. The wiggles are what you draw when you do this. Okay. So we got to get the wiggles right, but the one thing that we know is interaction of this graph. It's just going to take off to negative numbers. I mean, negative 2 to the fifth is 32, right? Negative 32, right? So negative 32 is pretty low. Negative 3 to the fifth is negative 81. Okay. Negative 4 to the fifth. Anybody want to guess what that is? Let's say when I did negative 3 to the fifth, I actually said negative 81. It's negative 243. Okay. Negative 4 to the fifth is 1024. So as we got to negative 3, negative 4, negative 5, negative 6, this thing goes down very, very rapidly. And we go to the positive, where it goes up very rapidly. You want to understand that, so now we understand that this graph has to come up from the left, and it has to go up to the right. You know what I did? I was a little concerned about this. Yeah. The graph that I drew here would be from negative x to the fifth. And when I decided to draw it from this side, that was because it's easier to pull the chalk than it is to push it. No, actually. Forget it. The graph was right. I don't know what I was looking at over here, but yeah, the graph goes down here and it goes up here because that's what x to the fifth does. Now, if we draw the graph, then we've got to come up, down low, go through here, go through here, go through here, and go through here, and end up high. That works out just fine if you draw this. Okay. But it doesn't act like this when x equals -2. Because of this, it acts like an x cubed function. Okay. There's our behavior. And right now I'm just going through these. This isn't the graph of this function. But this is the way everybody wanted to draw the graph when we started. It's not far off. Okay. Let's look at what happens at -2. Then we'll talk about what happens at 3 and 5, because that was the question. Okay. At -2, this comes from the x plus 2 cubed, right? This is a 0. I'll say this 0 is due to the factor x plus 2 cubed. What does the graph of x plus 2 cubed look like? It looks like your cube graph shifted 2 units to the left. So if this is x cubed, then -2 is here. You horizontally shifted -2 units. Now, one of you asked, when I get my zeros, -2, 3, and 5, do I change their signs? No, the zeros are where they are, but your instinct was, well, you change signs. Well, if your zero is at -2, that means if you shift a function -2 units, you replace x by x plus 2. Okay, and you were thinking that. So that's a rule for the transformation. Now you got to understand that rule for transformation to understand why. And you might not totally understand that every time you do it, but that's the explanation for why this thing flattens out at x equals -2. So the graph actually comes up like this. I'm going to okay, it's going to do something like this. So let's This isn't gonna be your highest point. Your highest point's actually gonna be over here a little further. Didn't want to draw the graph through my label. Then we'll try it. Thus, the graph is probably gonna look more like this. But we're not looking for artistic accuracy. Okay. If you draw it, as long as it flattens out here, goes through this point, through this point, through this point. That's good. And of course, if you're shown a graph like an open math, to show you a graph, and that's what the equation is. You gotta recognize, well, that's probably a cube. If you've got one like does this, like the red graph here, and that's probably a square, and so forth. Well, we could do a lot more examples, but we want to. We're running into problems on this because we need to understand the distributive law better and how to expand polynomials, so we understand why you get an x cubed or an x to the fifth out of this. Of course, we need to be able to do the arithmetic. We got to know what our basic graphs look like. Put those three things together, and this is hard to understand. And the procedure again, what did we do? We found the intercepts. Y-intercept happened when x equals 0. X-intercept happened when y equals 0. So we understand that. The long run behavior, you find the highest power of x, and then you ask yourself, is that an even power or an odd power? It's an even power, it's going to look like this. The higher the power, the flatter it is. It's an odd power, it's going to look like this. But of course, the higher the power, the flatter it is. Then you can sketch a graph. Got to act like the highest power when you zoom back, which is why it goes way down here and way up here. And it doesn't flatten out. It doesn't come up here and then tail off. It keeps getting steeper and steeper. And to understand that, you really need to understand the arithmetic. Making a simple table. Okay. You just make a table for power function from -2 to 2. And do that accurately. Then you begin to understand how the numbers drive this behavior. And if you don't understand that, then it's harder to see what to do. Okay. You might memorize how to do it. But you won't really understand it. Okay. Now we're almost out of time. And I really wanted to talk about long division. But again, we ran into several issues. Make sure you kind of make note of those issues and do some practice. Okay. I'm going to talk briefly about long division. Okay, so x plus 2 goes into this. We're going to imitate the long division algorithm, which you probably haven't used since you were in 5th grade. Hopefully it made an impression on you then. Okay. What do we need to multiply x by to get x cubed? We're going to multiply by x to some power. What power of x do we multiply by x itself in order to get x cubed? X times what equals x cubed? Not going to be x squared. Okay. Not sure I saw it too. I think I saw 1 and a 3. We average those. It's correct. So we have to understand exponents. If I divide x into x cubed, I get x squared because x squared times x is x cubed. Then x squared times x is x cubed. X squared times 2 is 2x squared. if you remember your long division algorithm, you know, that you subtract this from what you have above it. So I'm going to put a little minus sign here. I'm not changing right here. Okay, I put a minus here to remind myself to subtract. I'm not changing the plus to the minus. Plus is a plus. But this is a reminder that I need to subtract. Then this is a reminder that I need to subtract. Now, if I subtract x cubed from x cubed, I get 0. If I subtract 2x cubed from 6x squared, I get 4x squared. I got 4x squared plus 8x. Now, what do I have to multiply by x to get 4x squared? I want to make this 4x squared go away. What do I multiply by? Well, I multiply by 4x. This 4x times x gives me 4x squared. Really, I just disproved something. Yeah, I made a mistake over here. Okay, well, anyhow. So I got 4x squared plus 8x. Now, what happens if I subtract all this? It all goes away. I get 0. Then I bring down the plus 8. Remainder here is 8. And then I put plus 8 over x plus 2. Now you'll see more of that in pre-calculus class when we get to it. You have an assignment on it, and Open Math explains it step by step. But again, we have the difficulty that people weren't really able to tell me what would multiply by x to get x cubed. And you really have to get that straight, and you can't address that here today. So there's stuff you kind of need to review. Okay. Okay. What do you sketch this graph? We'll do that. We'll talk about a graph that we sketched. In the support course. Read this very similar. Okay. And here is a set of things you've got to look at. Okay. You want to find the intercepts. Y-intercept occurs when x equals 0, the x-intercept occurs when y equals 0, something you can never not know. Okay. Any graph, you have to know that. Long run behavior, you find the highest power of x. Now, this is giving people a lot of trouble because people are having trouble with the distributive law. Okay. So you have to know the distributive law. I'm just going to kind of take a short list. A distributive law, probably also. Yeah, well, okay. I don't know the distributive law. And you have to understand that when we expand this using the distributive law, which we did in class, and there it is, but I made a mistake down here. 2 times 4 is 8, that should have been 8x. and 8x and 4x and 12x. And I'm not gonna go through this process, but when I did this, I should have had a 12x here. The 12 here. And the 12 here, which means instead of this 8, I have a 12. Then I have a 12x squared and minus 18x squared. Give me making 6x squared. And you don't have to follow this. I'm just doing this. So if you look at this, which will be part of your video, will hopefully be right. And then I have a negative 36x instead of negative 24. And I have then 8x minus 36x would be minus 28x. So anyhow, maybe that's right, maybe it isn't. This is how you expand it, and we can't take time in this class to relearn the distributive law, okay? And apply it. So make sure you understand how the distributive law is used, and there's probably still a mistake in here, some places and numbers. So don't let that throw you off. Make sure you understand how the distributive law works. So if you understand that, then you understand that when I square x plus 2, which I did down here, I get an x squared. Because x plus 2 times x plus 2, I know I'm going to multiply the x by the x. Then when I multiply by the x again, I'm going to have an x cubed. So I'm going to end up with an x cubed if I do this times this times this. And then if I multiply by x minus 5, well, actually by x minus 3, I'm going to get an x to the 4th. And when I multiply that by x minus 5, which I didn't do, and you can do that yourself, I'm going to get an x to the 5th. We have to understand that happens. Okay? You have to understand why we get an x to the 5th out of this. Now, that's the step. We say find the highest power of that. And that tends to give people a bit of trouble. Read the open math explanation, you can look at the expansion that I did in the preceding class, review it if you're in that class. Okay. Now we're trying to sketch a graph of this function. What's the highest power of x that you're going to have in this function? If I expand that, what's the highest power going to be? Oh, I didn't record any of that. I did it so wonderfully. Well, maybe not. Okay, well, copy this down and do it, and I'm gonna. Oh, man. I ran my mouth for over 20 minutes and didn't record any of it. Look at what the world has lost. I'll get over the tragedy here in a second. I'm gonna copy that down and do what I say. One more I wrote. Okay, well, hopefully we got this copy done. Okay. Let's sketch a graph of this function. Now I've got it down here, but kind of a mystery, but did a detailed graph, for this function, and support course, and that video is run together efficiently. And process, find the intercepts, check the long run behavior, and consider the degree of each zero. And if you got that process down, it's not very difficult. Once you have a factored polynomial, to graph it. Okay, so then of course we do this for homework. So here it is. Here's the polynomial we want to do. The y-intercept occurs when x is 0. So we plug x equals 0 in this expression and we get -45. Okay, so there's our x-intercept. So we can put -0, -45 in the graph. Y is 0. Well, in order for y to be 0, one of these things has to be 0. So it could be the first one, x minus 1 could be 0, x plus 5 could be 0, x minus 3 could be 0. We solve that. Well, that occurs if x equals 1 or x equals -5 or x equals 3. So now we have 3 points here. Now, what people want to do at this stage is connect these points, go through this one, come back through this one, go down through this one. Okay? And you can't do that. Why can't you do that? Well, if you go down through this one, you can't get back up. And you got to get back up. Why do you have to get back up? Well, you got to get back up because if you expand this expression, you're going to get an x squared out of the x minus 3 squared, and you're going to have to multiply that by x, among other things. You're going to have to multiply that by 2. You're going to have to multiply that x squared by x to give you an x cubed. And then when you multiply by x minus 1, that x cubed is going to get multiplied by x to give you an x to the 4th. This is going to act like x to the 4th. So the long run behavior is y equals x to the 4th plus a bunch of stuff. And you can expand it. If you do it accurately, like I didn't previously, but I fixed it. Well, that's the way it's going to be. Okay. Actually, now if we zoom back and look at this thing from a great distance, the graph is going to look a lot like the x to the 4th graph. Okay, and the x to the 4th graph looks like this. We've got to understand why. We've got to be able to make tables for x cubed, x squared, and then extend on the x to the 4th and x to the 5th. So you really understand how these graphs behave. If you don't understand how the numbers work, give you a graph, you need to practice that until you really do. Point then is, the graph is going to look like this. It's going to have wiggles in the middle. Okay, so there's some wiggles there. And the wiggles look like this. Why do the wiggles look like this? Well, because we got to go through or hit at least all of these points on the x-axis. We can't go through them all. As we go through them all, we don't end up going up on this end, and the graph is not going to match the x to the 4th graph if we zoom back on it. So we know that the graph has to go up here and up here. And then we know the multiplicity, because the third thing I list here is consider the degree of each 0. Okay, the multiplicity would have been a better word. But it's the degree of the factor that gave you 0. And in this case, the degree of the factor that gave you 0 at 3, 0 is 2. Meaning that near this point, the graph acts like the basic toolkit squaring function x squared shifted 3 units to the right. That's where x minus 3 squared would be. Now, it's got other stuff in front of it, so it's also vertically stretched. But I sketched, before I sketched the graph, I sketched kind of a little parabola here to remind myself that the thing has to behave like a parabola at this point. And then we get the graph that looks like this. So that's the process. And if you look back at the support course, we did some expansion. We reinforce the distributive law. In order to understand what's going on here, you absolutely have to understand the distributive law, not just this for almost everything you do. And people still have difficulties with that. Have to understand this toolkit functions in order to understand this zoom back behavior. Understand transformations, then you understand why you have something that's parabolic at x equals 3 at 3, 0. And of course, got to understand that. Okay. Well, then we went on. Go along with it. And again, if I ask what has to go here, multiply x to give us an x to the 4th, not everybody saw that. Okay, you really have to understand exponents, and we explained that. We're not going to go back through that explanation, but here's the process. Okay, x cubed times x gives us x to the 4th. X cubed times 2 gives us 2x cubed. Okay, we put little minus signs here because we're going to subtract this expression from this. We haven't changed the sign. We just put a little reminder sign up here to remind us that we're going to do 3x squared actually minus 2x cubed. That gives x cubed. Then x squared times x gives an x cubed here, and x squared times 2 gives us 2x squared. Again, we put little reminder signs up here. And we got a negative 8x squared, and negative 8x times x gives us a negative 8x squared. Negative 8x times 2 gives us negative 16x, and so on. And we follow the process down to the point where everything in this case works out. There's no remainder. So we know that x plus 2 goes into this many times. We checked. Is x plus 2 times this equal this? Because x plus 2 goes into this many times, then this times this equals this. Okay, well, we worked it out using this derivative law. X plus 2 times this is x times this plus 2 times this. We multiply through, we get these terms, we add them up, and we get x to the 4th plus 3x. We get all this, which matches this. So we've checked, we've proved, and you want to check these things. Prove. So at this stage, we've established that x to the 4th, well, this polynomial that we had under the, that we divided by x plus 2, this polynomial then equals x plus 2 times the x cubed plus x squared minus 8x minus 4. Okay, that's I asked that you, wherever it is. That long division, we determined that this thing, that's the thing we were dividing into, this polynomial equals this times this. From this, we know that if x equals negative 2, the whole thing is 0. Now, question, we find a 0 of this quotient. Okay. If we find a 0 of this, and we got another 0 of the f of x function. Well, everybody find one? What was it? Yeah, okay, it's negative 2. Everybody find that? Substitute negative 2 for x. This whole thing is 0. So we lucked out. We fairly quickly found a 0. Now, that's not always going to happen. And if it's a real world polynomial, it's never going to happen. Okay. So this is kind of not all that applicable in the real world, but we need to understand it for other purposes. Okay, so we found that this doesn't work. This doesn't work. Well, let me put those. No. No. Yes, okay. Well, that means that x plus 2 is going to divide that polynomial. Okay, well, we do that. A little shorter than the last one, it's not difficult. Okay, I'm gonna put an x squared here, since x squared times x gives me x cubed. Then, of course, x squared better multiply that too. Red chalk. And we'll subtract, we'll subtract. We're gonna end up with negative x squared minus 8x. Okay, well, then we're gonna have to have a negative x up here. The negative x times x is what's gonna give us negative x squared. We have negative x squared and minus 2x. Okay. Then put a little minus sign down here. Then we get negative 6x minus 12. And x plus 2 goes into negative 6x minus 12. Well, x goes into negative 6x, negative 6 times. Because negative 6 times x is negative 6x. And that's minus 12. And this matches, so we're done. Okay. So now we have this. In other words, this equals this times this. And no, it doesn't, because I copied down the wrong line thing again. You better wake me up. Okay. Gives us x squared minus x minus 6. Okay. Therefore, f of x equals, well, we determined f of x was x plus 2 times this. And we determined that this, which is this, is equal to this. So now f of x is x plus 2 times x plus 2 times x squared minus x minus 6. Well, then, you know how to factor this. This is just a trinomial. We get x minus 3 times x plus 2. And then we write that as x minus 3 times x plus 2 cubed. And now we can graph it. Have 0 at negative 3, have 0 SR at 3, and a 0 at negative 2. Go ahead, graph it. A little bit of room right here. If x equals 0, in the original form, I see that we get y equals negative 24. So I get my y-intercept at -24.0. Then the highest power is the fourth power. Now, if I had it in factored form and didn't have it in that form, I would know that the highest power is the fourth power. Because if I cube x plus 2, that's x plus 2 times x plus 2, which would give me an x squared. And another x plus 2 would give me an x cubed. And multiplying by another x is going to give me x to the fourth. So I get an x cubed out of this, an x out of this gives me an x to the fourth. So it's got the same behavior that we saw previously. Got to go up here. Got to go up here. Also, if this zero, or sorry, at the zero here at -2, it's going to act like a cubic function. So the graph is going to do this. It's going to come down here. We'll level off from this, come on down here and kind of go a little ways further before it comes back up. And if we know the process, we practice by doing half a dozen problems. And doing them, without watching the video at every step. In other words, you watch the video, you think you know how to do it, put the video away and see if you can do the next problem. Okay. And if you can't, go back and look at the video and keep that up until you can do them without looking back. Then a couple of days later, go back and do a couple more to make sure you haven't forgotten it. And then when an exam comes up, quick review, you should be able to do it. Okay. Lock these things in. Spend more time if you need to. Make sure you're approaching it correctly. The goal of homework is not just to get a right answer and get a point. Homework doesn't count that heavily, although if you blow it off, you're going to probably lose at least a letter grade. Okay. But more importantly than the credit you lose is that you're not going to learn it. And when test time comes, you're out of luck. Test time's coming in 2 weeks. Okay. So get into it. Practice that long division. Open Math shows you exactly what I just showed you. Get the process down so you don't have to watch a video every time you do a problem, right? Because I think I'm seeing evidence of that in a lot of work. And of course, some of you aren't doing the homework and got to do that. Okay, if you're doing the homework, you can just modify what you're doing a little bit and I think do real well. Okay.